says that the dimension of the kernel of a linear transformation plus the dimension of the range of a linear transformation is equal to the dimension of the domain vector space. All right. Yes, Landon?
You said something about like beta var something dealing with three nature. Could you say that again, like one more time?
Oh, I'm saying the reason we change coordinates is to sort of see what linear transfer, to find some way of characterizing a linear transformation which really reveals what it really is. It helps us see past our particular choice of coordinates, which could muddy the real nature of what we're looking at. So the proof of this basically is I mean, I'm not going to have time to really go through it properly, but essentially all this proof is you know, you pick a basis for the null space to start with, right? I pick a basis for the null space in the domain, and then I take that basis and I extend it to everything else, all right? Everything that's not in the null space basis has to be vectors of the form that end up mapping to the image, non-trivially. So the image, and basically this is what's proved, is that the image of everything that's not in the part of the basis which corresponds to the kernel, rather, linear transformation, so everything that's not in the basis for the kernel, those vectors end up giving you images which have to fill out the range. So then it's just counting. You've got the number of vectors in the basis for the kernel, everything else, and that gives you the number, basis for the range. So if you just say number of vectors in the kernel, number of vectors which map to the range, which is the same as the dimension of the range, that gives you dimension of kernel plus dimension of range, but the basis we're talking about is a basis for V. So what I'm trying to tell you is this might look like a scary proof, but if you actually take 20 minutes to read it carefully, you'll find out it's really simple. And it's just using the basis extension theorems that we already have. Maybe I'll spend 10 minutes talking through it another day. I wanted to show you something really interesting though. So tied to that proof when you understand it is this theorem. If V and W are vector spaces over a finite dimensional vector space over reals, and if T is linear transformation from V to W, and if the rank of the linear transformation is P, in other words, the number of linearly independent, the dimension of the column space, right, or dimension of the range, I claim those are the same, then there exists spaces beta for V and gamma for W such that the linear transformation can be written as the identity matrix, a P by P identity matrix padded with zeros. So, if I have a linear transformation T from V to W, right? And if I look at T, say with respect to one choice of basis, beta gamma, then basically it's P inverse the matrix of T with respect to another basis, Q, or you could just say P and Q if you don't want to use P inverse here, whatever. The point is, let me just say, well, find P. I mean, I don't know. It's somewhat relevant. Two matrices, let me just make it more simple. Say B is equal to P, A, Q, or P and Q invertible. Such matrices, A and B, are said to be matrix congruent. Matrix congruent. So, what this says, and you can prove that that's an